today we'll be looking at the area volume question from the 2000 exam. This was question number 1, and it is a calculator active question. And they've been kind enough to provide us with a graph here of the functions that we're going to explore. It would appear that the intersection of these two curves is at x equals 1, but we should never make any assumptions. We should actually go about finding that intersection point should we need this. So first part A is asking us to find the area of the region. So the area of our region is going to be the integral from where the region starts to where the region finishes of the top curve minus the bottom curve. So our top curve is e to the negative x squared, and then the bottom curve is at 1 minus cosine of x. Put those in parentheses. And we have our region provided we find the value of a. So that a is where these intersect. So we need to find the location of the intersection. And so what we're going to do is set one equation equal to the other equation and rely on our calculator to find these values. So the intersection is at x equals, and we're going to turn to our calculator. So let's grab our calculators and find this piece of information. Okay, so what we're going to need to do is go to our grapher, and let's clear out any equations that we have already in the y equals. Our first equation is e to the negative x squared. So e raised to the negative x squared for our y1, and then our y2 is 1 minus cosine of x. And we want to make sure that our mode is set to radians. Calculus class, we use radians. And if we graph this equation, we should get something similar to the graph that they've provided us. So there's the 1 minus cosine x in blue, and then e to the negative x squared in red. And it looks like the intersection between the two graphs occurs at 1. But we need to verify for certain it occurs at 1 because it may occur at some value other than 1. So if you press second trace, that will pull up the intersect menu, option 5. And we can move our cursor close to the value that we're interested in finding an intersection. First curve is the blue one, press enter. Second curve is the red one, press enter. And then finally, we're guessing this intersection point as opposed to the one over here. So we hit enter when we're close to that one. And we get an intersection at x equals 0.941, as I suspected, just shy of 1. So 0.941, we're going to go ahead and store that in our calculator for use later. I'm going to call that variable a. And just on the off chance that we need the y-coordinate, I'm going to also press alpha y, and we'll store that as the letter b. So if I need to call on these variables, they're now stored in a and b. All right, back to the work. Now that we've found the value and stored it under a, we can use our calculator to also evaluate the integral expression. So by pressing Math 9, we pull up the definite integral. We're going from 0 to a, and our top curve I stored in y1. So by pressing alpha trace, I can pull up the y1, and then alpha trace again will pull up y2. That allows me to access the pre-typed in equations. You can also manually type in the equation or access the y1 and y2 by pressing vars, scrolling right to y vars, selecting function, and then those things exist there. So once we've typed in our integral expression, we can evaluate this, and we get an area of 0.5909. So equals 0.5909. For the AP test, a value of 3 decimal places is suitable. So 0.590 or 0.591. They'll accept rounded or truncated. And these are approximations because we're doing the rounding process. But there's our Part A completed. The breakdown for Part A is you get 1 point for having the integrand correct. So the top curve minus the bottom curve, that's worth 1 point. You get 1 point for having the answer correct. There's also an additional point that comes from, it says, having the correct limits in the integral in A, B, or C. So I've established the limits for the integral in Part A, so that's going to also net me a 3rd point there. So let's look at Part B. Part B is a volume of revolution. And so we're taking this same region and we're going to rotate it around a horizontal line. Let's take a look at a computer graphic for this. All right, so for Part B, we are doing a volume of revolution or volume of rotation, and we're going to take this region and rotate it around the x-axis. So that yellow region gets swept around the axis. You can see one of our washers forming here in blue, and then as we sweep that washer to the left or right, we're going to get the total volume recorded. So that's the region that we're trying to capture, and we're going to sum up the area of each of these washers to create the volume of the entire region. Or rather, the sum of the volume of each washer, where the height of the washer is delta x. All right, so our volume is going to be stacked along the x-axis. We have all these washers stacking up along x. A loose sketch here. We have a slice that then spins around and creates that washer. And the big radius is going to be the distance from the top function to the bottom rotation line, and the small radius is the bottom function to the rotation line. So our general go-to equation for volumes of revolution is going to be pi big R squared minus little r squared. These are stacked up from x. So there's our general case there. To make it specific to this, we're going to take our boundaries. The washers stack up from 0 to that point that we called A, so 0 to A. The big radius is the top curve minus the rotation line, which happens to be at 0 in this case because it's on the axis. And our little radius is the bottom curve minus the rotation line. So our little radius is going to be 1 minus cosine of x. Let's subtract 0 from that, just to be consistent. Subtract 0. There's our integral expression that will calculate the volume for the solid when we rotate it, and we need to then include our constant of rotation, pi, almost forgot that, and then turn to our calculator to evaluate this. I'm going to clean this up just a bit because the zeros wind up disappearing. E to the negative x squared, and 1 minus cosine of x squared dx. And again, we have this stored under y1 and this stored under y2. So if we turn to the calculator, all we have to do is take this expression and we're going to change y1 to y1 squared. And y2 to y2 squared. So let's put parentheses around the y1, square it, and then put parentheses around the y2 and square it. And this will give us our volume of revolution times pi, or our answer times pi. So this is equal to 0.55596 pi, approximately. And if we multiply that on the calculator, we get an answer of approximately 1.746, or 1.745 if you're rounding. And that's the final volume of revolution. Part B is worth, looks like 3 points, 2 points for the integrand and constant, and -1 for each hair, and then 1 point for the answer. So 2 points for the integrand, 1, 2, and then 1 point, and constant. Let's double check that again. Oh, integrand and constant. So we have to be sure to include that pi. And then the third point comes from the answer. All right. Part C is a volume of perpendicular cross sections. So let's make a rough sketch of this so that we can build out our volume of perpendicular cross sections. Oops, my rounding was off there. 1746, and then this rounds up to 1746. Okay, fix that error, and our perpendicular cross sections, I'm going to kind of flatten out the drawing. So we have one curve coming up like this, another one coming down like that. Our z-axis is now kind of a vertical line there, and what's happening is we are having cross sections that are perpendicular to the x-axis, and they are being extruded to a square. So this shape here, you get a square, and we'll call this length s of x. And if it's a square, the height of that square is also s of x. So the area of one cross section is base times height, or just s of x squared. If we're going to do the volume of one cross section, the volume of one cross section would be s of x squared times our delta x. And if we're doing that, then our delta x is however thick our slice is. And then we introduce the world of calculus, where we make our delta x very, very thin by taking the limit as delta x approaches 0, and we can create the volume expression for all of these square cross sections. So each square cross section is put in like that, stacked from 0 to a. And I need to identify what is s of x. So this is 0 to a of top curve minus the bottom curve squared dx. That is our volume expression there. And they ask us to find the volume of the solids, so we need to then turn to our calculator and plug this equation into the calculator. So it's very similar to what we've done in the past. Instead of y1 being squared and y2 being squared, what's going to happen is the difference of y1 minus y2 gets squared. Our boundary is still 0 to a, so we're going to do that. And we come up with an area of, a volume of approximately 0.461. And in reflecting upon my notes here, I realized I used a capital A here. So in all of my problems, I have to make sure that my boundary is with a capital A. This should have been capital A. And this should have been capital A. And now we have a little bit of a conflict there, but we'll just cross those lines out and voila. So this is worth, part C is worth 3 points as well. The first 2 points comes from having the correct integrand, and then the third point comes from having the correct answer. And they make a note here that 0 of 2, if not of the form one function minus the other quantity squared times a constant. Because if you paid attention to cross sections, all of our cross sections wind up being of this form, top function minus bottom function squared times some constant. And that constant depends on whether we do square cross-sections, semicircle cross-sections, triangular cross-sections, etc. So that's the total of 15 points. A couple notational errors that I made along the way, but I picked them up. Sorry about that. Be sure to comment, like, and subscribe. Have a good day.